So what we want to look at now is the concept of rotational inertia. So just like we had regular inertia, which kind of gave us the idea that an object in motion will want to stay in motion, in straight line motion at constant speed, or at rest unless acted upon by an outside force. Well, we have the same concept in rotation, that an object rotating wants to continue rotating or be at rest unless acted upon by outside influences, by external influence. And this is our rotational inertia. Now we know that rotational inertia must be slightly different than regular inertia. If it wasn't, we wouldn't have it. We would just call it inertia still. So what we want to do is we want to think about rotational inertia and how is it different than regular inertia and why do we need it? And we can start by thinking about the fact that when we have an object, certain objects tend to rotate more easily or more, you can get it going more easily, or the object's much more difficult to get rotating. And a simple example to start by thinking is thinking about like baseball and having a baseball bat. So like when you have a baseball bat, usually the sweet spot of the bat is near the top. That's where most of the mass is located. And so when you're like swinging your bat, if you wanted to increase and make the bat easier to swing, what do they tell you to do? If you want to speed up your swing, they tell you to choke up on the bat. Well, that means when you choke up on the bat, that essentially brings your hands closer to that sweet spot at the top of the bat, and then you're able to swing the bat faster. And that's because the bat has some type of rotational inertia based on its mass. And so the other part to think about is, as you're swinging the bat, your hand position relative to that sweet spot on the bat changes how easy or difficult it is to swing the bat. If you rotate and you hold the bat by the thick end and swing it, it's very easy to swing because you're making the rotation point near most of the mass. So when we're thinking about rotational inertia, rotational inertia is going to depend, one, upon the mass, because it is inertia, but it's not just the mass, upon the mass and how it's distributed. How it's distributed about the rotation axis. And the rotation axis is simply where you want to rotate the object about. And so, too, it's the mass and how it's distributed about the axis into the axis you're rotating about. So these are kind of the two things that are going to determine our rotational inertia. And rotational inertia has a little special symbol that we set aside for it called I. So I is the rotational inertia for an object. And what we're going to do is we're going to look at how the distribution and the rotation axis affect these things. So let's take a look upon the distribution around the axis. So when we're thinking about this rotational inertia and the mass distribution, we can think of two things. You can think of having a solid disk and then a hoop. So this is kind of like a solid disk, and then this is some kind of thin hoop. And only the mass of the hoop is kind of distributed along the outside, and it's empty in here. Now, if the center of rotation is there, and both of these have the same mass, and same radius, what it turns out is this is solid and a hoop, solid disk and the hoop. What it turns out is if objects have the same mass and same radius, for this distribution, whenever the mass is closer to the center, mass is closer to rotation, it has a lower I. So the idea is the disk actually has more mass. If we're rotating it around that central point, the disk actually has a lower I because more of its mass is closer to the center. The hoop has this mass, this radial distance away. This one has more of the mass closer to here. That means it has a lower I. If we were to race these down some kind of incline or across something, it turns out that this one would win because it can get rotating. It has a lower I, so it can get to a higher rotational speed more quickly. This one will take a little longer to get to that same rotational speed, but what happens is once it gets there, it's harder to stop. So the idea is that whenever the mass is closer to the rotation axis, it has a lower I, as long as you're comparing the same thing. Now, if we change the radius of the hoop or we change the mass of the disk, that may no longer hold. But for a given distribution, if the objects have the same mass and radius, whatever, then whenever you move the mass away, this will have the higher I. The higher I. This one would have the lower I. And so what happens is the moment of inertia depends on the mass and how it's distributed. When the mass is closer to the rotation axis, it has a lower I compared to when the mass is further around. Now the other part we were talking about with this, just as we have the hoop and the disk here, if we change the rotation axis on this, and instead of being this way and have the hoop do that, if we change the rotation axis and we make it vertical on the hoop, and let's now compare hoop to hoop. When we compare hoop to hoop, if we have another hoop, let's assume that I could draw well, and my hoops would have been the same size here. That's closer. So if we have another hoop that's identical, they have the same mass and same radius. This one we rotate about this point, about center. This one is about, we're going to kind of rotate it, like imagine taking a ring and having an axis and then rotating the hoop around this way. So it's going to rotate like that, about this axis. Well, using our thought process from before, because we're changing the rotation axis and where we're rotating, this one now, when we compare these two hoops and how we're rotating it, this one has the higher I. And we can use our first thought because this one has what? Now this has some of the mass closer to this rotation axis. So this one, if we're comparing the eye of these two of the same ring based on different rotation axis, this one will win. This one will have the lower eye because some of the mass is near the axis. And this gets to that second point that choosing your rotation axis, because you're choosing how the mass is, changing how the mass is distributed, it changes the eye. So let's take a look at, let's say, this marker. This marker actually can have multiple rotation axes. You could rotate if we took an axis and drew it down the line of the pencil coming towards you, the pen, the marker, and we rotate it this way about that axis, that's one of the rotation axes. We could drive an axis through the center of the marker and rotate it this way. And then we could just take it and rotate it in a circle about the end, like this, which is hard to do for me. So we take it, and based on those three different rotation axes, the moment of inertia for the marker is different. The one where it comes down the barrel of the marker, and we're rotating it this way, that's the lowest, because it has the most mass closest to the center. When we do this one, this is the next lowest, because this has the most mass closest to the center of the axis. When we do this one and go on end around, this should have the highest moment of inertia, because we have very little mass near it, and we have mass farther away from the center of rotation. So thinking about how the mass is distributed and which axis we choose determines our moment of inertia. Now, in general, what you usually, for most objects that you will encounter, the moment of inertia can be found in a table somewhere. Your book has a list of, most physics books have a list of moments of inertia for various objects. But this is the idea. The moment of inertia is the ease or difficulty to get an object rotating, and then it's also the ease or difficulty to stop the object once it's rotating. The moments of inertia will depend upon the mass and how it's distributed. The more mass closer to the center of the axis of rotation, the lower the eye is going to be. And of course, for a given object, you could choose various axes to rotate about, and that will change the eye because you're changing around the point of rotation how the mass is distributed.